So one issue was, for example, you drew your state diagram and you should have had a 1 here, but you had a 0, right? And in almost all those cases, if I look up in your table, you actually had a 1, right? You actually had the 0 that you were supposed to have, and it was just a transcription error going from your transition table to your diagram, right? And that's really easy to do because this all kind of blurs together after a while, especially at the end of a long homework set. But you got to write in the table, right? That's the most important thing. The other error that I saw was errors in filling in these columns, but your equations were correct. And again, that's just kind of pilot error, right? That's trying to do the and of two things, but you did an or for some reason. And that doesn't concern me, because that's just a silly error, and that's why we have computers, right? We don't do this on the job. The computers do it for us. We have to do this part. We have to come up with the equations. We have to interpret the diagram. But filling in truth tables, right, we got to know how to do that so we can be tested on it. But in general, if you understand how to do that in principle, I'm not worried if you make a mistake here and there. So that's good. Along those lines, something that I did see that I do want to mention so that you can try to do something different. For example, you come up with an equation like, let's say, J0 equals Q1 bar or Q0 bar X all barred. All right, and you're filling in your truth table. So you've got Q1, Q0, and you might have these in whatever order. And you're trying to fill in the J0 variable. So, okay, well, Q1 bar is a 1, and Q0 bar is a 1, and X is a 1, 1 or 1 is 1. That's a 1 complement, that's a 0, okay? There are so many ways you can go wrong like that. Especially, again, at the end of a long problem, or when you're time crunched, like working on an exam, you're going to inevitably make mistakes in here. Okay, so here's how I recommend filling out these truth tables. Don't jump straight to the thing you're after. Break it down into pieces. Okay, Q0X. Well, make yourself a column for Q0 bar. It's going to take you 15 seconds to do this. It's a little bit of time, but all you got to do is complement Q0. 1, 1, 0, 0. 1, 1, 0, 0. And now make yourself a column for Q0 bar ANDed with X. And when you do this, you're thinking, okay, I've got to take this column and this column. Where are they both 1? That's where I'm going to have a 1 in the output. Well, that's going to happen in the second spot and this spot down here, and that's it. Everything else will be a 0. And now, go ahead and make a column for Q1 bar. Yeah, it's just this thing inverted, but put it in a separate column. So flip those. And now we can make a column for this expression. Q1 bar ORed with Q0 bar X. Well, it's just taking these two columns and doing a logical OR. So if either one of those is a 1, we want a 1 in the output. Well, that's pretty easy. Looks like that. And now you can fill in J0, and it's just the complement of this column. So 0, 0, 0, 0, 1, 0, 1, 1. And if you do that carefully, you're almost guaranteed to get the right answer there. It's a few more columns. This is why I keep saying get yourself a nice wide sheet of paper and a really fine point pencil, right? And take your time, sink into the process, right? And if something goes wrong at the end, it's really easy to come back and figure out where you made a mistake. But there's a really good chance you won't make a mistake if you do it in these steps, right? Because at each step you're doing something that you've known since 120. How do I OR two variables? How do I AND two variables? And your two variables are right here or right here, right? So save yourself the trouble of trying to do everything in your head. And you got to practice that on homeworks, right? So that when you get to an exam, you know how much time you have, you know how much time it takes to do this versus doing it in your head versus getting it right as opposed to getting it wrong, right? So you develop these skills at doing these kinds of problems. And you'll definitely see state machine problems on the final. Okay, there will definitely be an analysis question like this. There'll definitely be a synthesis question like homework 5. Okay, so the time you're spending doing the homework sets and working on these things is well spent. Okay, because it'll be a fairly good chunk of the final exam. Was that a question for me?
Oh no.
Okay.
Just throwing
All right, so I think people are in good shape. I think you got the technical aspects down pat. So that's encouraging. All right, so questions about the homework I just handed back, homework for state machine analysis, or questions that we didn't grade. I think we talked through these on Thursday, right? So any other questions on homework 4? So how about homework 5? So this is the one you're working on right now. This is due Thursday. And we're going to spend time after this going through state machine synthesis in detail. And I've got your new version of a quick guide, and that's posted on Canvas. So we're going to do the same thing we did before. We're going to go to the board in groups and work on some of these. But let's talk about general questions with this homework first. Yeah?
I don't really understand what they're asking us to do in question 3.
All right, so question 3. Design a synchronous finite state machine that performs present state and next state in accordance to the following table. So this is a different way of describing a state machine, right? We've talked about starting from a state diagram. And here you're kind of starting from a state transition table. So you have 2 states, A and B. And it looks like you have 2 bits of input labeled X and Y. And depending on which state you're in and what your input is, you go to your new state of A or B, and you also generate an output. So first of all, is this a Mealy machine or a Moore machine? Do we remember what the difference is?
More.
It's Moore. Why?
It's my guess. I don't know.
It's a good guess.
50% chance.
50% chance. So what's a Moore machine?
The inputs stay the same?
Something like that. The output stays the same regardless of the inputs. So a Moore machine, the outputs only depend on your state. A Mealy machine, they also depend on the inputs. So in this system, the output is shown. If you're in state A, the output is 0. If you're in state B, the output is 1. And it doesn't matter what you put into your inputs, 0, 0, 0, 1, 1, 0, or 1, 1. Your output is 0 in state A, it's 1 in state B. So that's a nice, solid Moore machine. And we could draw a diagram for this. So I'm going to show 2 states. And since it's a Moore machine, the output can be shown inside the state. And so I'll put a key down here. So I'm naming the state, and then I'm listing the output Z. And there's 2 inputs, X and Y. And so we should have 4 arrows coming out of each of these states for the 4 combinations of X and Y. And it looks like if you're in state A, we transition to A or B depending on the value of Y. So 0, 0 brings us back to A, 1, 0 brings us back to A. and the other ones bring us to B. And if we're in state B, it looks like 0, 1, and 1, 0 leave us in B, and the others bring us back to A. So something like this. So that's the state diagram corresponding to that question. And sometimes it's useful, even though they're giving you a transition table, to draw a state diagram just to be starting from a familiar point. But really from here we're going to build up a transition table which is going to include this somewhere inside it, right? But we would typically write this out as 2 states, 4 input combinations, so 8 rows of a transition table. And then from there we do the thing that we're going to do every time that we design a machine. And so the subparts on this derive minimum excitation and output equations for the full encoded design using T flip-flops and show the implementation. And we haven't talked about one-hot encoded design yet. I said I would tell you about that today, so we'll talk about that presently. But all of these questions are basically saying, come up with a circuit diagram. Okay, but to do that, you need to figure out what the inputs of the flip-flop should be, and then come up with equations for those, minimize them, simplify them, and then sketch a circuit. So let's talk about this full encoding versus one-hot encoding. So you've got 2 states, and we'll call those A and B. So how many flip-flops do you need to encode 2 states? 1. So we just have a single flip-flop, we can call it Q. And we could say if it's a 0, then we're in state A. If it's a 1, we're in state B. You could do it the other way also. So 1 flip-flop lets you encode 2 states. But there's a different way we could code this. Which is to use 2 flip-flops. And we could say in state A, Q1 is a 0, Q0 is a 1. In state B, Q1 is a 1, Q0 is a 0. Now, why would we want to use 2 flip-flops when we can get away with 1? There's no real good reason here. But let me show you a different example. Suppose you have 4 states, A, B, C, D. So minimum is 2 flip-flops, right? 2 to the second is 4. All right. We can design a machine like that. We know how to do that. Suppose that state A is the idle state. Say we're controlling a motor, okay? A is the idle state, and B is the state when we want to run the motor forward, and C is the state when we want to run the motor backwards. And D is the state when something goes wrong, and that's the emergency stage. So we've got a motor, it's driving some huge piece of equipment. If it's not doing anything, we're in state A. When we go to state B, it's moving forward. When we go to state C, it's moving backwards. If something goes wrong, if it detects an energy spike, if the black hole containment field is starting to fail, we switch to state D. That's the emergency state. It sets off alarms, it evacuates the town, etc., etc. Okay? So here's what's happening. You're running along, your circuitry that you built in 250 is running this system, and it's going forward. So you're sitting in this state right here. And now somebody wants the system to go backwards. So they type in some commands, and what's going to happen is Q1 is going to become a 1 and Q0 is going to become a 0. What happens if Q0 changes first before Q1 changes first before Q0 changes?
Alarms.
For a brief period of time, we're in state D. And it's temporary, but it may be long enough, depending on what this state is hooked up to, that may be long enough to be in that state that you trigger some unwanted consequences. So this is a glitch possibility. So here's how we can deal with that. We can have a totally different coding using 4 flip-flops. So this is called one-hop encoding. One-hop meaning that there's exactly one flip-flop that's outputting a 1 in any valid state. So suppose now we're going from this state to this state. So that's our forward state. This is our ending state. And again, suppose this flip-flop changes first, so that briefly we're in this situation. That's not a valid state. And we're going to make sure that if we're in a state other than one of these valid states, we don't generate any outputs that we don't want to generate. So the only time we're going to come into this state is when this bit over here becomes a 1. And in moving from this bit to this bit, it's never going to change value. So it's a kind of inherently glitch-free way to number your states, to code your states, that prevents you from accidentally entering another state that you didn't intend to. Because when we move from one state to another, one valid state to another valid state, we turn off one bit and we turn on another bit. The bit we turn off is the one that was on right now, and the bit that we turn on is the one that we want on eventually. And we're never going to turn on any other bits. So we'll never accidentally think that we're in state A or state D in this case. Yeah?
So when we're in the, when it goes from transition, the one you 0, 0, 1, 0 to 0, 1, 0, 0, the one in between, when it goes to that, nothing happens, right?
Nothing happens because that's not a recognized state. So when we do our state diagram, right, the unrecognized states would basically be no ops. It would put the outputs in safe conditions, and it's a transient state. Eventually we'll come down here. The only time we can get into danger is if we come into this state. And for that to happen, this bit would have to turn on for some reason, and that's not going to happen going from here to here. We're only worried about possible timing mismatches where one of these bits changes before the other. And that won't take us into this undesirable state. So that's one-hop encoding. It takes more hardware, but it's more resistant to glitchy behavior like this. And it actually gives you pretty simple circuits to design because we end up with a lot of don't cares when we do our transition table. But with 4 flip-flops, that table's going to be pretty big. On the other hand, when we're doing this on the job, right, we're really not doing this ourselves. We've got software doing this for us. And so if we have 4 flip-flops or 10 flip-flops, that's not a problem. If it makes sense from a design perspective to do that, we do that, and we let the software figure out the details for us. So that's what's going on in here. Part A, they want you to use full encoding. Okay, that's using one flip-flop with different combinations. Part B, they want one-hop encoding, so a single flip-flop turned on at any time. But the process from that point on is identical. All right, other homework questions? Or other questions on this?
Just gonna set up. I had trouble kind of understanding how to set up number 2. It's like the state diagram.
Yeah. Oh, yeah. So binary counter from 2 to 7 and back to 2. Well, how many states does this machine have? 6, right? So it goes from, one state to the next, to the third, fourth, fifth, sixth, and then it's kind of back to the first state. And we know the pattern is going to repeat, so 6 states will suffice.
So which is like an up counter from 2 to 7.
So it's an up counter from 2 to 7, and we can name our states whatever we want. And pretty much each transition, we're just going to move to the next stage.
Is there any reason why you'd ever stay in the same state?
Not on this problem, but very good reason in general, right? You might want a counter that you can pause. And so you could have a run/don't run input. And then if you're in the pause state, right, you would just idle in whatever state you're currently in. And that's a very reasonable design to work on, and you can buy chips that do that. So we can name these whatever we want. I'll be boring. But we can list outputs, and our outputs here would just be 2, 3, 4, 5, 6, 7. And there's no input. And so our key is really just state. And then output. So how many bits of output do we need?
3.
1 or 3? Or maybe 2. Probably 3. Because we have 6 different values we have to output. So that's at least 3 bits, and if we just output the numbers 2 through 7, right, 0, 1, 0 through 1, 1, 1, so 3 bits will work. And there's no input, so we just show what state we transition to next. So that's your setup, and then you have to build it once using D flip-flops, once using T, and once using JK. Probably pick on that one or number 1 for. We'll probably pick on number 1 at the board. Other questions? Mm-hmm.
Yes, so number 5. I'm just having trouble reading state diagrams and making sense of
Very good.
Okay.
what's going on.
Yeah, the happy sad machine.
Yeah.
Okay. So we've got 4 states, right? 4 bubbles. We have 1 input X and 1 output Z. So on these transition arrows, the key always says input/outputs. So X is an input, Z is an output. So in words, suppose you're in the reset state and your input is a 0. What's your new state going to be? So your state is either reset, happy, sad, or so-so. So if you're in the reset state and your input's a 1, you're following this arrow, you stay in the reset state. If your input is a 0, that's the thing before the slash, your next state is happy. If you're in the happy state and your input's a 1, what's your next stage? Yeah, the 1 says you're just going to follow this arrow, you're going to stay in this stage. Okay, what if your input's a 0? Is that making sense?
Yeah, like
Well, so if you get that, and you get what the outputs are also, so if you're happy and your input's a 0, your output's going to be 1, and your new state is sad. Well, once you have that, right, this is no different from this, right? There's no inputs here, and there's no outputs other than the state outputs, the more outputs. But it's really just saying if you're in this state, your next state's going to be B. If you're in B, your next state's going to be C. In here, if you're in this state reset, your next state, if your input 0, is going to be happy. And if your input's still 0, it's going to be sad. And if it's still 0, then you're going to stay in this state. And once you have a transition diagram like this, right, our goal is to build a transition table. And then when we have a table, we can use that to sketch a circuit. But it should feel pretty much the same as, say, questions 1 and 2, except that 1 and 2 were phrased in the language of systems we're already familiar with, like up-down counters.
Yes, maybe I'm just not understanding how we're determining how many bits we have.
How many bits for what?
Just like when we're doing like the truth table.
Okay, so how many states do we have?
4,
So how many flip-flops do we need to code 4 states?
2.
2, right? We can code them 0, 0, 0, 1, 1, 0, 1, 1, 4 combinations. So 2 flip-flops. So let's put some of this down. So 4 states, 2 flip-flops. Does it tell us what kind to use? JK, okay. How many input bits do we have?
1.
Just 1, it's just X, and X is either a 0 or a 1. So we have 1 input. And how many output bits do we need? Just 1, because it looks like every output is either 0 or 1. So 1 output. So the specifics you have to fill in from the table, but our general table is going to look like this. So present state. And do they call the input X and the output Z? Yeah. So 1 input bit is X, 1 output bit is Z. So present state and X. And there's going to be 4 possible present states, and for each of those there's 2 possible X's. That's going to give us 8 rows. And then for each of those, we're going to have an output bit, and we're going to list what the next state is. So these are the parts we're just going to fill in all combinations, and for each of those, based on the diagram, we're going to fill in what the output is and what the next state is.
So we only have an input if we're told that there's an input.
Yeah. And you're either told in words, or you can look at a key and you can see, you know, something before the slash, and you'll see it on these transition arrows. And it might be 1 bit, it might be 3 bits, could be any number of bits. And your output, if it's a mealy output, if it depends on the input, it's listed on the transition arrow after the slash. If it depends only on the state, it's usually listed in these bubbles underneath the name of the state. All right, so you want to work this one out as a group up here, and then we can break, and then we can go on the whiteboard and you can work on some other problems together. Okay, so I posted this on Canvas. This is the synthesis version of the handout that we did last week. So 8 steps, more or less. Step 1, decide how many flip-flops you need. Okay. And if you're doing full encoding, it's just whatever number lets you have 2 to the n be at least the number of states. Decide what kinds of flip-flops, which generally you're going to be told. use JK flip-flops, use D flip-flops, okay? But if you're doing this for yourself, you can decide what kind of flip-flop to use. And then make a state assignment table. So if you're using full encoding, then combinations of your flip-flop outputs correspond to each state. So you got to make a table and say, state 1 has this combination of outputs, state 2 has this combination of outputs, or state A or state happy or whatever. Okay, so you come up with that on your own. It's whatever you want. Okay, you'll get the same place in the end. And then the big step, make a state transition table. So you're going to have one row for each combination of state and input. So present state and inputs. For each combination, you have a row in your truth table. And then list the outputs and the next states. And that comes from your diagram. And then you can throw away your diagram and just work from here. And so step 6, this is the synthesis version of the weird step in analysis, right? Based on your understanding of the types of flip-flops you're using and your knowledge of what the current flip-flop values are and what you want them to be, figure out what the inputs of the flip-flops need to be. So if it's a D flip-flop, you just set it to whatever you want the new state to be. If it's a toggle flip-flop, you decide whether you need to toggle or not, and so on. So list the flip-flop inputs for each row and fill in the flip-flop values based on present state, next state, and how flip-flops operate. And then you've got a good old 120 truth table. You've got inputs, not inputs, but you've got 3 things that determine which row of the truth table you're in, and you're going to have values for all your flip-flop inputs. So write equations for those. Minimize them, use K-maps, whatever your favorite approach is, so that you end up with equations saying, for example, J1 equals something, K1 equals something. And then when you've got equations, draw a circuit that implements those equations, and you're done. So let's do this for that particular homework question. And let me put this up here so that we can refer to it. So this is reset. This is happy. Sad. So 1 takes you there, a 0 takes you there. Happy, a 1 moves you here. A 0 takes you to sad. Output a 1. Sad, a 0 leaves you here. Output a 1 takes you to so-so. And so-so, a 1 takes you back. And a 0 takes you to reset. Okay, barring transcription errors. That's what we're working with. All right, so first step, how many flip-flops do we need? So how many flip-flops should we use? Let's use 2. We'll make our lives easier. So 2 flip-flops. And what kind of flip-flop should we use? Should we stick with JK since that's what the problem asked for? Okay. It takes more work to use JKs, but the work is a little easier along the way because we usually get don't cares. So we'll go for JKs. All right, so we have 4 states. We need to make a state assignment table. So let me put that over here. So we've got reset, happy, sad, and so-so. All right, 2 flip-flops. I'm going to stick to the convention we've been using throughout. We're going to number these starting from 0. And we're going to call the flip-flop outputs Q. So I'm going to label these Q1 and Q0. Okay, so assign states to combinations of flip-flop outputs. And don't try to do this with the inputs, because you'll go down a totally different path. Okay, so we want the outputs here. We can do any assignment we like. It makes no difference in the final circuit. I always kind of go in order just because I'm a creature of habit, but you don't have to. All right, now we're preparing to write a state transition table. So one row per combination of state and input. So present state and input. So our input is X. Totally did not leave myself enough space. We may not take this all the way to the end because I think you're going to have the hang of it before we get there, and I'd rather you do this on the board. Okay, agreed. Those are the only 8 possible situations, right? We got to be in one of those 4 states, and our input is either a 0 or a 1. So I want to list my states in terms of these Q variables. So let's put those columns in. So all of this, these are basically the 8 rows of our truth table. It's combinations of Q1, Q0, and X. All right. List the outputs and next states for each row. So our output is Z. And we fill in Z by looking at the table. So if we're in the reset state and our input is 0, our output is 1. So this is a 1. If we're in the reset state and our input is a 1, this says our output is a 0. So what if you're happy and your input is 0? What's your output? 1. And if you're happy and your input is 1, right? So there's the 1. Input is 1, output is 0. If you're sad and your input is 0, output's 1. That's on the upper right. Sad and the input is 1. Your output is also 1 there. And if you're so-so and the input is 0, output's 1. So-so and input of 1 is 0. That's this one right there. Output of 0. All right, you got your Z filled in. We're almost done. Let's fill in the next state. So reset and a 0, your next state is happy. Reset and an input of 1, your next state is reset. So everyone's got the idea on this column? All right, we're just reading off from here. So happy, 0 takes you to sad, 1 leaves you happy. Sad, a 0 leaves you sad. Sad and a 1 takes you to so-so. So-so and a 0 takes you to reset. And a 1 takes you to sad. And check in while you're doing this, right? What exactly are we writing down? This is our present state. This is our input of 0, takes us to our new state of reset. Okay, so state 0, input is 0, new state is reset. All right. And then we want to list the next state in terms of the Qs, right? So the Q pluses, as we've been calling them, Q1 plus and Q0 plus. And again, we're just transcribing from our state assignment table. So happy, or reset is 0, 0. Happy is 0, 1. Sad is 1, 0. And so-so is 1, 1. Sad is 1, 0. That's your whole state transition table. So for each of these combinations of present state and input, we know what the value of z should be. We know what the value of q1 and q0 should be after the clock tick. Okay, we're almost done with the table. This is where your choice of flip-flop comes into play. So if we have a JK flip-flop, I'm looking at Q1 right now, we have a JK flip-flop and it's currently outputting a 0, and we want it to output a 0 after the clock tick. What do we set J and K to? So Q is 0, we want the next value of Q to be 0. So what was your answer?
0. They're both 0.
So you can set them both to 0 because that means don't change anything.
Or 0, 1.
Or we can say 0, 1, which means set the output to a 0. So 0, don't care. So J1, K1, 0, don't care. And then J0, K0, we do the same thing for Q0. So currently it's a 0, and we want it to become a 1. So yeah, we could do a 1, 0, which means set, or we could do a 1, 1, which means toggle. So that's a 1, don't care. Up there. And you do that 16 times. Right? But along the way, you write that little table maybe that says, if this is my current Q and this is what I want my next Q to be, what do I set J and K to? Or you go through this exercise until you feel like you can do this in your sleep, and now you don't have to study anything about JK flip-flops for the exam because you already know it, right? And you can concentrate on this stuff. All right, so you do this 16 times and you come up with all of these values. And now you're back to week 1. Here's a truth table. We consider these to be the inputs, the things that are going on the right-hand side of our equations, and these are the outputs that we want. Z, J1, K1, J0, K0. And you write equations. Z equals, J1 equals, K1 equals, K0 equals, J0 equals. And you do that by writing a sum of products or a product of sums or going into a K-map and minimizing and so on. And once you've got equations, that's what you sketch into your circuit. And then your final circuit is going to look something like this. Here's J1, K1, Q1. We always get Q1 bar for free, so we don't have to use inverters. Here's your other flip-flop. What do we do with the clock?
To the same clock.
Yeah, tie them together to the same clock. And then you're going to sketch a circuit that takes these Q inputs along with X, right, that external input, and ultimately generates something that goes to J1, something that goes to K1, something that goes to K0, J0, and Z. And you just get those from here and here. And there's your answer. So I don't want to spend time going through these up here. I want you to do those on the board. But given that we fill those in correctly, is everybody comfortable going from there to circuit diagram? All right. So let's take a 5-minute break. Let's come back at 5 till, and I'll have you break into groups, and we'll probably pick on question 1. And we'll start with D flip-flops. Okay, well, we'll go through it step by step in groups, and I have some reference guides. You can pick up one per group. All right, so I'll see you in 5 minutes.